Okay, so this is for us to know how to do differential calculus by first principle, and it's a very, very simple thing. Now, first principle just shows us how both terms in an equation, the independent term and independent term, changes that occur in them, and how to differentiate equations. Now, we'll take for example this function y is equal to f of x plus x. This simply means y is a function of x. So if I take that equation, y is a function of x, and I want to differentiate this is how we start. Now, x is an independent variable, while y is a dependent variable in this equation. Reason being that the value of y depends on what we assign x to, or what we assign to x. Now, let the change that will occur in x be referred to as delta x. This is change in x, while the corresponding change in y that results giving us delta y. So, a change in x equals a change in y. Therefore, y plus delta y will give us x plus delta x. Now we make delta y the summation of the formula. Delta y gives us x plus delta x plus, minus 1. Our delta y becomes x plus delta x minus y, which is equal to x in the numerator. So we're looking at this, we know x minus x gives us delta. So we have that delta y is equal to delta x. If I divide both sides by delta x, I get delta x here, delta x here. Delta y over delta x is equal to 1. Of course, delta x divided by delta x gives us 1. So this term here, delta y over delta x, is also referred to as dy dx, which is the derivative of any function y functioning as x, or y being a function of x. Now we can also check this for a more complex equation. Let's say y equal to 2x squared. You can check that. Let us say y is equal to 2x squared. Now, our change in x will cause a change in y. Therefore, y plus delta y gives us 2 into x plus delta x all squared. Now, mind you, it's not a change in x squared, it's a change in x. So that's why the function appears to. It's not x squared plus delta x squared. It is x plus delta x. Now, y plus delta y will give us, we have to expand this. So just to expand this is a very simple thing. X to the power of 2 plus x by delta x by 2, which is 2x delta x plus delta x also. This is what this expression gives us. Now, y plus delta. Now, we can make delta y the summation of the formula. So delta y equals 2x squared plus 2x delta x plus delta x all squared minus y. Of course, we know our y is both 2x squared. So it gives us 2, the open this bracket, it gives you 2x squared plus 4x delta x, 2 times 2 is 4, plus 2 delta x whole squared minus 2x squared. Looking at this equation, we know that 2x squared will cancel minus 2x squared. That leaves us with delta y as 4x delta x plus 2 delta x whole squared. Now, we can divide both sides by delta x. This will give us to delta y over delta x being delta x cancels itself here. It cancels here, it is delta x. So that gives us 4x plus 2 delta x. Now, we have to find the limits of this function because we do not need a change in x on this side of the equation. So, the limit of delta y over delta x as delta x tends to 0 is what gives us the y x. So, as delta x tends to 0, we are going to get an approximately equal value of the derivative. Now, it implies that the y, the x, is 4x plus wherever we see delta x substitute is 0. 2 is 0. Of course, this gives us 0. So the y x is equal to 4x. That is the derivative of this function 2x squared. So, having seen this in first principle, this first principle also helps us to find standard derivatives. What I want to mean by standard derivatives? In the first equation I saw, it was y was equal to x. That was just with myself. That's the standard derivative. So we found out that if y was equal to x, the y dx give us 1. This is the standard derivative. So we are going to look at other standard derivatives, and those standard derivatives can be gotten from the first principle. So now the first equation on the standard derivative we are going to look at is the function y equals to 8x to the power of n. Now this equation, what this equation is, y is a function of x here, but the x here has a coefficient which is a and an exponent n. So we want to know how to differentiate any function that appears in this format. Now, the derivative of this function is always given as a n x n to the power of 1 minus 1. What this means is that if I'm given this function y is equal to ax to the power of n, I simply multiply the power by the coefficient and subtract 1 from the power of x. In that way, I get my derivative. For example, as we solved initially, we said y was equal to 2 times 2 times x to the power of 2 minus 1. That gives us 2 times 2 is 4. 2 minus 1 is 1. X raised to the power 1 is x. That gives us 4x. This is what we solve this with differential position. So that is that. If we try another equation, say y equals to x raised to the power 3. Looking at it and comparing it, we find out that our a is 1. Here, because x cubed is the same thing as 1 times x cubed. So our a here is 1 and our a here is 3. So the y dx gives us 1 times 3 times x raised to the power 3 minus 1. That gives us 3x raised to the power 2. Without doing that, that's that. So the next one we are going to look at, or the next standard differential or derivative we are going to look at, is the trigonometric derivative y equals to sine x. Now, y equals to sine x. The y dx is giving us cos x. This is standard derivative. But we can use first principle to know it anyway. Now, I will show you from first principle how to get this result. If y is equal to sine x, y, we said before that let's change the x. The change in x will give us the corresponding change in y. So our y plus delta y will give us sine x plus delta x. Now, we'll make our delta y subject to the formula. Of course, delta y is equal to sine x plus delta x minus sine x. At this junction, we have to bring back or recall our trigonometric identities. This is a case of where we have sine A minus sine B. And this equation is giving us 2 cos A plus B over 2 sine A minus B over 2. So, this is what it's going to be. Now, if we look at this and open this up, we'll have that delta y is equal to 2 cos our a here being x plus delta x, x plus delta x plus delta x over 2 sine x plus delta x minus delta x over 2. So this gives us delta y is equal to 2 cos x plus 2 delta x over 2 sine delta x over 2. Now, if we divide, what do we do here now? We cannot divide completely. by delta x, or let's do it, we divide by delta x and we get delta x. So now, what we do here is to okay, there is a mistake here. I will remember we said sine A minus B. So sorry, here should be not delta x because B is x. So B is x. Here is also x, not delta x, sorry. So if we please, if we can follow from here, it is x plus delta x plus x and x with the x minus x. So if we do the arithmetic, we have x plus x is x plus delta x. While here is x minus x is 0. So we have only delta x here. Okay. So now we can, okay, so if we divide by delta x, this is what we get. Now we can express this as delta y over delta x. This gives us 2 cos 2x plus delta x over 2. If we just divide this, we have the same thing as x plus delta x over 2. While here remains sine delta x over 2 over delta x. Now, we can make this also become cos x plus delta x over 2 sine delta x over 2 over, here becomes delta x over 2 because this is not clear. So let me rewrite it again. Okay, so this thing gives us again, as I said, delta y over delta x is 2 cos x plus delta x over 2 sine delta x over 2 over delta x. Now, if we invert this, that is delta, if we invert 2 over delta x, it's the same thing as 1 over delta x over 2. So that's exactly what we're going to do here. So that becomes cos x plus delta x over 2 sine delta x over 2 over delta x over 2. So I can still make this cos x plus delta x over 2 multiplying sine delta x over 2 over delta x over 2. Now if we take limits to this function, we find out that we know very well that the limit of sine theta over theta as theta tends to 0 gives us 1. This is a normal function when we are doing limits. So if we take that same example and put it here, we find that this whole entity here gives us 1. So obviously our delta y over delta x, as delta x tends to 0, is cos x plus 0 over 2 times 1, since I've said the limit of this is 1. So that gives us cos x, because this times 1 is the same thing. 0 over 2 is 0, x plus 0 is x. So the derivative of sin x is cos x. So I will write out other derivatives, other standard derivatives that we all have to memorize, because most of them have to be memorized when we are going further into differentiation. So if y is equal to sin x, our dy dx gives us what? Cos x. If y is equal to cos x, the y dx, or its derivative, is minus sin x. If y is equal to the tangent of x, the y dx becomes the square of the secant of x. If y is equal to, let's use the inverse functions, inverse of these functions. If y is equal to, inverse of sin x is what we call cosecant of x. The y dx gives us minus x cot x. This stands for the cotangent. If y is equal to, in the inverse of cos x is the secant of x, the y dx becomes sec of x multiplied by tan of x. And if y is equal to the inverse of tan x, which is the cotangent of x, the y dx becomes cosec, or the cosecant square x. So this is what it is. So these are supposed to, this one is supposed to be memorized. Okay, we also have if y is equal to the exponential of x, e raised to x, this natural number. If we differentiate it, we get the same thing. That's the beauty about this one. Most of the times, if you differentiate this, you get the same value here. There are others, but we'll see all of them as we go on in this video. The next thing we're going to enter is differentiation of polynomials. Of course, you know what polynomials are. So, take for example, y is equal to x squared plus 2x plus 3. How do we differentiate this? This is quite simple. As we said before, if y is equal to a raised to the power ax to the power of n, our dy dx becomes a n x raised to the power n minus 1. So we'll use this to solve for each of the terms of this polynomial. So we can rewrite this polynomial for easy explanation in this format. X squared plus of 1 plus 3x to the power of 0. Of course, by the laws of indices, anything to the power of 0 is 1. So, let us differentiate. The y, the x becomes the coefficient of here, the coefficient here is 1. This is 1 times 2 x to the power of 2 minus 1 plus 2 times 1 x to the power of 1 minus 1 plus 3 times 0 x to the power of 0 minus 1. So this gives us 1 times 2 being 2 x to the power of 1, which is x, plus 2 times 1, 2. X to the power of 1 minus 1 is x to the power of 0. X to the power of 0 is 1. So this leaves us as 2. While this 3 by 0 already makes this entire expression of 0. So if we differentiate this function, this is what we get. So that is for an example in polynomials. So the next thing we are going to enter we are going to look at different methods that we use in also doing differentiation, because first and foremost, not all equations appear in this format I've shown you previously. Some of them appear as functions of functions, some of them appear as the product of two functions, some of them appear as a function being divided by another function. So we are going to see the different rules that apply for such kinds of functions. We start with the product rule first. For example, imagine having this kind of expression or equation. Y is equal to 2x plus 3 multiplied by 4x plus 1. Yes, for those who would think it straight, the first thing that comes to your mind is to open up the expression here and then use the formula or use the method of differentiating polynomials to do that. That also will give you your answer. But you see, the product rule is a very simple rule that enables us to differentiate this without having to express the expression, to open up the expression. So, take for instance, this is the product rule. Take for instance, y is equal to u multiplied by v, where u is the first binomial expansion or binomial expression, and v is the second binomial expression. U and v are functions of x. Y is also a function of x. Now, we find out that the y, the x, is given as v multiplying the u, the x, plus u multiplying the v, the x. What does this mean? It means a very simple thing. It means if you are giving a function that happens to be a multiple of two other functions, what you do is you pick the first one and multiply it by the derivative of the second, plus you pick the second one and multiply it by the derivative of the first. That's just what happened here. So it is v times the derivative of 2x plus 3, which is the u dx, plus u times the derivative of this, the u dx. So having said that, we can simply express, we can simply find the derivative of this function, and it's given as if y is equal to 2x plus 3, 4x plus 1, our dy dx gives us v is what? 4x plus 1 multiplied by, now we differentiate 2x plus 3. If I differentiate 2x plus 3, I'm going to get 2 plus u, which is 2x plus 3, multiplied by the derivative of this 4x plus 1. If I differentiate it, I'm going to get 4. So, having done that, we now open up the expression. This is 8x plus 2 plus 8x plus 12. That gives us 8x plus 8x is 16x. 2 plus 12 is 16. First. So this is the answer when you differentiate this function. So this is simply how the product rule works. You take the first term and multiply it by the derivative of, or you take rather one term and multiply by the derivative of the other, and then take the other term and multiply it by the derivative of the first one with 2. That gives us a very clear explanation as to how the product rule is. So we can also move to another type of method, which I will call the quotient rule. So the first one, the product rule, we put it as y equals to uv. In the quotient rule, it can appear in this format, or it appears in this format. Y is equal to 2x plus 3 over 4x plus 1. So in this case, y is equal to u over v. How do we do this? Now, the formula here is giving us dy dx is equal to v multiplying du dx minus u multiplying dv dx, all of them divided by the square of v. This is called the quotient rule. This is the formula we use when the equations or the expressions given to us to find the derivative appear in this format. So, having seen this, we can actually solve this. Remember, this is our u and this is our v. So, following that, the y x becomes v, which is 4x plus 1, multiplying the u dx, which is 2, minus u, which is 2x plus 3. The v dx, differentiating this gives us 4. We divide it all by d squared, which is 4x plus 1 all squared. So now, this gives us 8x plus 2 minus 8x minus 12. Of course, minus and plus is minus over 4x plus 1 all squared. Okay, so this gives us, of course, this will cancel this out. 8x minus 8x, 0. 2 minus 4 gives us minus 10 all over 4x plus 1 all squared. So this is the derivative of this function. So take note, whenever the function appears in this format where one term is dividing the other term, you make use of this. So I repeat it again. if y is equal to u over v, where both y, u, and v are all functions of x. That is the conditions for this. If these are functions of any other variable, then this formula is not applicable. But they are all functions of x. So the derivative dy dx gives us v du dx minus u v dx over v squared. It's a simple way to cram it, but it's very fun. Since we know u is the top term and v is the bottom term, this is how I would say it. I would say, if I'm giving this format or this expression in this format, I would say the y dx, which is the derivative, is equal to the bottom, the top, minus top, the bottom, over bottom squared. In that way you get it. Because we already know that u is the top, v is the bottom. So bottom, the top, which means the bottom times the derivative of the top minus top times the derivative of the bottom over square of the bottom. If you can get that, then it will be easy to memorize this formula. So I think that is all. You can also check other expansions and see if this works in the quotient rule. Of course, definitely it's going to work. The next one I'll show you is function of a function. Function of a function simply means in one equation we have two functions there. So let me show you how it works. Take for example, function of a function. I can also call this, or they also call it the substitution method, or algebraic substitution method. Now, this substitution method you can use in this function. Take for example a function like this: y is equal to sine 2x plus 5. How do we solve this? Because there are two functions here now. There is the sine function and there is the binomial function. Now, when we say function of a function, the binomial function is, or this function here is also functioning inside the sine function. So it is actually difficult to differentiate or find the derivative of this function by any of the methods that have been explained earlier. You can't do that. So we'll do what we call substitution. That's why I said it's also called substitution method. We say, for example, to reduce this, we tell ourselves, we introduce another variable. Let another variable, say u, be equal to 2x plus 5. If u is equal to 2x plus 5, it establishes one thing, that y therefore is what? Sine u. Have you seen now? It was first a function of a function, but now we have been able to break it down into two different functions. Y being a function of u, and u being a function of x. Now, we can differentiate. We differentiate this and we differentiate this, and then I show you the formula of how we get our original derivative. The u dx, if we use our normal, we know that differentiating a constant itself. Differentiating this, I have 2. While the y du, as we've said before, if y was sine x, the y dx is what? Cos x. the initial derivatives I told us to come. So the y du in this case will what? Cos u. Now, the y dx, which is our original derivative, is given as the y du times du dx. That is why we call it function of a function. So by substitution, we have been able to get this formula. So of course our dy du is what? 2. And our the y du is cos u, and our du dx is 2. So this gives us 2 cos u. Now there's just something that is remaining here. We are looking for this function in terms of x because y is a function of x, not u. So what is our value of u in the initial equation? 2x plus 5. Therefore, our dy dx is equal to 2 cos 2x plus 5. So that solves the answer. So if we differentiate this is what we are going to get. So that is it for the substitution method, because that is how it is done. So just know very well that whenever you see a function like this, probably tan or probably log or natural logarithm, you know very well that you have to make a substitution with the initial algebraic term here or any other term inside here, so that you can separate them into two different functions and then get your derivative. Also, looking at this function, we could also, for fast learners, you could also differentiate this function and skip all these methods. How? Take for example, we said before, y is 2x sine 2x plus 5. There is a way to do this. It's still the same method, but it's somehow faster. This is a sine function and this is a binomial function. What do we do? Y is equal to sine 2x plus 5. If I differentiate the sine function, what do I get? A cos function. So the y dx is equal to, if I differentiate sine, I get what? Cos 2x plus 5. Because I'm differentiating the sine function. Sine of this, if I differentiate it, I'll get the cos of this, of that same thing. Now, if I differentiate 2x plus 5, I'm going to get 2. So I multiply it times 2, which gives me what? 2 cos 2x plus 5, which is the same as the original answer we got. So, for those who can catch up with this, if you can catch up with this, it's even better. It helps you, it's quicker to use and solve. But it still does the same thing. Of course, this is, if we put it here, we said this was u. So the u dx was 2, while the y du was cos u, which is cos 2x plus 5, as we said initially. So that's it for the function of function. Okay, let us try maybe another function. See, let us take let's use a more complex one. Let's use a tan. Let's say tan 3x squared plus 4x minus 1. Let's look at this. So, we'll do the same, like I said before. The standard derivatives I told us previously to memorize, if we check them, we find out that if I differentiate the tangent function, I'm going to get the square of the second function, which means the y dx is what? The square of the second, sec squared 3x squared plus 4x minus 1. Now I also have to differentiate this. If I differentiate this, I have 6x plus 4. So what does it give me? 6x plus 4 sec square 3x squared plus 4x minus 1. This is a simple answer. So for any function that appears in this format, you just use the same method. I think the next we'll be going to is the logarithmic functions. The logarithmic and the exponential functions. We're going there. These are the ones that are more interesting. Very, very interesting. We've been dealing with equations that have x as the variable. But now we're going to do it in the case of logarithmic and exponential equations. We'll be dealing with x as an exponent, as a power. Logarithmic and exponential functions. Okay, so we'll be dealing with 3 different formats of these functions. Take the first example. Y is equal to a to the power of x. Now, we've been dealing with x as a variable, not in this case, but it's a power now. So, in this case, a is just a constant. A could stand for 10, 100, 29, 1 million, any number. It's to the power of what? X. How do we solve this? We know that by the laws of indices, if we take the ln, the natural logarithm of this function of both sides, we'll have that ln y is equal to x is equal to ln a to the power of x, and that this also means ln y is equal to x to the power of ln a. Okay? So, how do we do this? Now we have to differentiate. Rather, we have to differentiate. Now, okay, now, if we look at this, which means we likely have to look at the logarithmic part first of all before we go to the exponential part, so that we can follow along. So let me, first of all, deal with the first equation. Sorry about this. I'll deal with the first equation. Y is equal to log x. And also, y is equal to log x. Now, I'll deal with this first. Now, if y is equal to ln x, ln x means y is equal to log x to the base of b. That's what this means. By the law of indices, this means that x is also equal to e raised to the power y. That's what this means. So, If we look at this now, I'm just going to do something a little bit odd from what we're doing normally, but it's still the same principle. We'll be dealing with the y dx. The y dx simply means the change in y with respect to change in x. But here, for me to get this expression, I have to do with the change in x to the change in y. So we're not talking about the y dx, and we're talking about the x dy, which gives me what? If I differentiate this function, remember when I said if y is equal to e raised to power x, if we differentiate it, we get the same function. So differentiating e raised to power y with respect to y, it gives us the same thing. So the x dy gives us this, which implies that the y dx will give us 1 over e raised to power y. E raised to power y is what? X initially, which means our dy dx gives us 1 over x. Which means if y is equal to the natural logarithm of x, the differential is what? Or derivative, sorry, is what? 1 over x. So if I differentiate ln x, natural logarithm of x, I get 1 over x. So that will help us here to know the derivative of this function log x. Now, log x means ln x over ln 10. How? By the laws of logarithm, we know that log a to the base of c, take for instance, is equal to log a to the base of b over log c to the base of b. That's what this means. So in this case here, our base is 10. It's 10. So log x to the base of 10 is the same as log e to the base of x over log e to the base of 10. And if we look very well, this is an expression, while this is a constant. So we'll use what formula now, if we remember, the quotient rule to solve this, which implies that, which is the y dx, of course this is our u, and this will be our v. The y dx is equal to v du dx minus u dv dx over v squared. So our v is ln 10. If we differentiate this ln x as we've done here, we'll have 1 over x minus u, which is ln x, into dv dx. Remember I said this is a constant, and if you differentiate the constant, it's 0. So this is 0. Over v squared being ln 10 all squared. So this gives me 1 over x ln 10 over ln 10 all squared. Of course, this cancels out, even ln 10 here. This gives me 1 over x ln 10. So this is the derivative of the log function. 1 over x ln 10. While this is the derivative of the ln function, 1 over x. Memorize this because we are going to use it in the exponential equations. Now, the first exponential equation we are going to use, we're going to deal with is y is equal to a raised to the power x. We also deal with y is equal to e raised to the power x. Now, if y is equal to a raised to the power x, a to the power of x, we can take the of both sides, or should I say rather the log, it means that x is equal to log y to the base of a, which means that x is equal to ln y over ln a. So like I did before, I will be differentiating x with respect to y in this case for simplicity. So this is still our u using the quotient u, and this is our v. So the x, the y gives us what? V du dy minus u dv dy over v squared. This gives us, what's our v? Ln a. Du dy, differentiating this gives us 1 over y minus u ln y, differentiating v. This is a constant, obviously. A is a constant, so ln a is also a constant. That gives us 0 over v squared ln a or squared. If we look at this, we'll find out that we are going to get 1 over y, we are going to get the x, the y as 1 over y ln a. But we are not looking for the x, the y, because the original function y is a function of x. So the y dx will overcome the equation, gives us y ln a. What was y in the original equation? A raised to power x. Therefore, the y dx is equal to a raised to power x ln a. So when you have this equation in this format, this is our derivative. Now, from there, we can actually find the derivative of e raised to power x. Although I have said it before that differentiating this function gives you the same answer. So we said here y is equal to e raised to power x, and here y is equal to e raised to power x. If we substitute e for a in this same equation, we are going to get our derivative because it's almost the same thing. So whenever we see a in this equation, we put e. So if for the case of e, the y dx will be equal to e raised to power x ln e. And of course, ln e means log e to the base of e. And if you remember in our laws of logarithm, the logarithm of a number to its own base is 1. So this becomes what? 1. So this is e raised to power x times 1, which is e raised to power x. Explaining why the derivative is the same as the function. So if we differentiate this, we get this. If we differentiate this, we get the same function. Okay, we are done with exponential and logarithmic functions for a start. We can go to implicit functions. And now, the definition of implicit function is not really hard. All the equations we've been solving are explicit functions. Now, explicit meaning there is a clear dependent variable and independent variable. In implicit functions, what we have is multiples of both the independent and the dependent variable. For instance, if you are told to differentiate a function such as this, xy squared plus 2y cubed equal to 4. I should find the derivative of this function. That is differentiate y with respect to x. How do I do this? Now, I think for some of us who think, and if you look at this equation, you can't really make y the subject of the formula, so it's difficult to make y the subject of the formula here to stand alone. So this is what we use the method called implicit differentiation to get the y dx value here. So what do? The rule is, in equations like this, the rule is very simple. You pick a term and differentiate that term with respect to x, leaving the other term as a constant. And then you differentiate that same term again with respect to y multiplied by the y dx. This is what I mean. Solution: differentiating with respect to x. You're going to have, I said, first of all, differentiate this with what? With respect to x. If I leaving the other term as a constant. So if y squared is a constant here and I differentiate x, I'm going to get y squared. Because if I differentiate x, I get 1 times y squared, which is y squared. Now, I differentiate the function again with respect to y, multiplied by the term dy dx, which is this. If I differentiate y squared with x as a constant now, I'll have 2y into x multiplied by dy dx plus, I do the same for this function. I differentiate this function with respect to x, leaving y as a constant. So which means all we have here is a constant, and differentiating a constant we have what? 0. Now I do again. I differentiate the constant, the expression with respect to y, x being a constant. If I differentiate it with respect to y, I'll have 6y squared dy dx. Differentiating 4 is a constant, so 0. Differentiating constant is 0. So we pick all the terms that have the y dx together and take the other ones to the other side of the equation. So what do we have here? We have that 2xy dy dx plus 6y squared dy dx is equal to y squared here is 0, so it's nothing. But y squared here going over here becomes minus y squared. The y dx is the common factor here. So the y dx into 2xy plus 6y squared is equal to minus y squared. We'll come over here. To make the y dx now the subject of the formula, we have that the y dx is equal to minus y squared all over 2xy plus 6y squared. We can still expand because y is a common factor under this denominator here. So this gives us minus y squared over 2y into x plus 3y if you factorize. Of course, y into y squared gives you y. So this gives you as the y dx is equal to minus y over 2 into x plus 3y. So for an implicit function like this is how we get the derivative. This is it. So this comes in handy, this particular method comes in handy when we enter the applications of differentiation. especially because when we deal with tangents, normals to conic sections, most conic sections have their equations in this format. So this principle of implicit differentiation helps us to differentiate such functions. So the last thing I will be showing today is higher derivatives. Now, higher derivatives simply means if I differentiate the function and I get the y dx, I differentiate that function I got as an answer to get another derivative, which is now known as the second derivative. So the second derivative is the higher derivative, and you can differentiate further as you can go. So for example, let's say higher derivatives. Let's say we have a function like this. Y is equal to sine 2x. So we have a function like this. And they said we should find maybe the second derivative, or the third derivative, or the fourth derivative. How do we do that? It's just quite simple. Of course, the first derivative is the y dx. The first time we differentiate it. How do we differentiate this? Now, this is also, like I said before, this is what in this case, it's a function of a function. We have two functions here. We have the sine function and we have a binomial function. Or a polynomial function, as the case may be. So how do we do this? If I differentiate the sine function, I get what? A cos function. Cos 2x. Multiplied by, I differentiate the binomial function inside, I differentiate 2x, I get 2. This gives me 2 cos 2x. That's the first derivative. First derivative. Now the second derivative means just to differentiate this function again, which means, and our second derivative is written in this format, the squared y dx squared. So how do I differentiate this? I differentiate this very simply. This is a constant, to bring it down. It doesn't really affect when we are differentiating. So if it's a constant outside any of the functions, it doesn't affect the differentiation. You just bring it out. And then, in our standard derivatives, if we remember, if I differentiate a cos function, I get a negative sine function. So I get minus sine 2x. And I now also have to differentiate this 2x, which leaves me with what? 2. So if I multiply all throughout, I have what? Minus 4 sine 2x. This is the second derivative of this function. If we have to go for the third derivative, we differentiate this again. I think from here you should get minus 8 cos 2x if you differentiate it just the normal way we differentiate functions of functions. So that's higher derivatives. You can also test and know what we do. Okay, let's do something more challenging. Let me use the tangent function is always challenging, very, very challenging, because it's tangent. Let me use the function y equal to tan x and find the higher derivatives. Of course, in our standard derivatives, we know that the y dx, if you differentiate the tan function, we get the square of the second function. Now, let's get the second derivative, which is a little bit difficult. Now this means the second all squared. That's what it means. So, if we differentiate the second function, we have to get what? The tan function, the sec function. If we differentiate this function all squared, we have to get it as what? 2 sec x. Remember, if we differentiate x squared, I get what? 2x. If I differentiate x squared, I get 2x. If I differentiate the function now inside, this is what we get from our standard derivatives. So, we get this as, if we multiply it, we get this as 2 tan x square of the second x. Do we go further? Okay. The cube y dx cube, which is the third derivative. Now, this third derivative is more complex. We are dealing with a function of a function here, probably, and we're also dealing with the product rule here. So, we have to do so. Now, remember, this is our u, and this is our v. Our u is tan x, our v is square of the second x. Now, remember I said whenever we have constants outside these functions, you just bring the constant out. It doesn't really affect the differentiation, just bring it out here. So, bring it out. The formula for product rule is what? V du dx plus what? U dv dx. So v is what? Sec square x multiplied by du dx. If I differentiate this, I get what? Sec square x plus u and x dv dx. So we have to differentiate sec square x. Remember, when we differentiate sec square x here, we got what? 2 tan x sec square x. So it's tan x into 2 tan x secant of the square x. This is what we get. So this gives us, if we open the expand, if we open the bracket up, we have 2. Okay, don't open there. Sec. Okay, let's look at it again. We have 2 sec square x times sec square x plus 2 tan square x sec square x. This gives us 2 sec square x into sec square x plus tan square x. Well, if you want to follow the rules of trigonometry, we can further expand this, but I suggest we do it this way. But if we do expand, of course, we know very well that sec square x is equal to 1 plus tan square x. This is it. This is the relationship between these two. So if we put this in that equation, we're going to get 2 sec square x into 1 plus tan square x plus tan square x, which gives me 2 sec square x into 1 plus 2 tan square x. So this is the third derivative. If you can continue further, if you do wish. Okay. Then we can look at the hyperbolic functions. Hyperbolic functions are very, very tricky as as compared to the okay, so like I said, the hyperbolic functions are written in this format, and each of them can be expressed in exponential form. So since x is represented in this format, cos x is e to the power of x plus e to the power of minus x over 2. Of course, we know that the tangent function is always sine this over cos of this, which gives us if you do the difference, if you do this is e raised to x minus e raised to minus x over 2 all over e raised to x minus plus e raised to minus x over 2. This gives us e raised to x minus e raised to minus x over 2 by 2 over e raised to x plus e raised to minus x, leaving us with e raised to x minus e to the power minus x over e to the power of x plus e to the power minus x. So obviously, this is what tangent x is expressed as. So I'm just going to show the differentials for this, and that will be all. So how do you differentiate this? If you differentiate this now, we find that the y, the x is equal to, differentiate this, of course, over 2 is half being the constant there, so we don't bother about it. So differentiating e raised to power x, we still have e raised to power x. But now, we're supposed to differentiate e raised to power the negative x. So I'm just going to do that for us. Make sure that when we do the differentiation. If y is equal to e raised to power of the negative x, this means that y is 1 over e raised to power x, of course, by the laws of indices. So the y dx using our quotient rule is v du dx, which is 0, minus u dv dx, which is, if you differentiate this, is still e raised to power x over v squared. This gives us, here is 0, here is minus e raised to power x over e raised to power x whole squared. That gives us minus 1 over e raised to power x, which is minus e raised to power minus x. So if I differentiate this, the y dx is minus e minus x. So we can put that here. So differentiating this, it will be minus e raised to minus x over 2, which gives us e raised to power x plus e raised to power minus x over 2. Of course, if you look at this, it is similar and the same to this. So that tells us one thing. If we differentiate the hyperbolic sine hx, if y is equal to sine hx, it means that the y dx is cos hx, cos x, as we call it. Let's differentiate this. Let's differentiate with cos x. So if we differentiate it, we know that the y dx for cos is what? E raised to power x plus, differentiating this, we have minus e raised to power minus x over 2. This gives us what? E raised to power x minus e raised to power minus x over 2. Looking at this, we know it's the same as the sine function. So therefore, if y is equal to cos x, the y dx is the same x. So that is it. We can also differentiate this. Anyway, if we differentiate the hyperbolic term, you're supposed to get, just like as in the logarithmic function, you're supposed to get the square of the second, but in this case, the hyperbolic function. That's always there. So for other functions, for other trigonometric functions, that's the inverse functions, they will still give us the same answer, only there is a difference. And trigonometric functions, if I differentiated sine x, I'll get cos x, yeah? Which is the same here for the hyperbolic. But in the trigonometric function, if I differentiate cos x, I'm going to get sine x. That's your x. If it was in the trigonometric, it would be negative here. But for the hyperbolic, it isn't negative. So, which means if you're differentiating the inverse of the sine function, of the cos function, which is the second function, you should be having a negative there. So I think also all you have to do is you have to identify, and yes, try the other ones and see what answers they do give you. And at least this is the basics for every other functions you can meet when you are dealing with differential calculus. Thank you very much.
Well, next time we'll be taking, today we did differentiation, the next class will be integration. Thank you for watching, and don't forget to subscribe. Thank you.